Hey everyone, and welcome. So today, we're going to talk about something that's literally happening all around you, right now. Heat transfer. You know, it's this hidden engine that powers everything from the food you cook to the weather outside your window. So yeah, let's get right into it. All right, to get our heads in the game, let's think about a couple of things. Ever wondered why your cooking pans are made of metal? Or how you can feel the warmth from a campfire even when you're sitting a few feet away? Well, the answers to both of those questions, they all point to the three basic ways that heat gets from one place to another. Okay, first up, we've got the most straightforward one, conduction. Think of it as the touch transfer. It's all about heat moving through direct contact. And this experiment here, it shows conduction in action perfectly. You see that flame heating up one end of the metal strip? Well, that heat starts to travel, kind of like a wave right down the metal. And as it gets to each of those little pins held on by wax, the wax melts and plink, the pin drops. Look at the order they fall in. It's such a great visual of heat literally on the move.
So, what's actually happening here? Well, the key thing to get about conduction is that heat is passed from one tiny particle to the next, almost like a line of dominoes. The first particle gets hot, starts vibrating like crazy, and bumps into its neighbor, passing on that energy. That neighbor then does the same thing to its neighbor, and so on, all the way down the line. But here's the kicker. The particles themselves aren't going anywhere. They're just passing the energy along.
Now, of course, not everything is as good at this as metal. That's why we use metal for our cooking pans, right? They're what we call good conductors. They let heat zip right through them. But then you've got stuff like wood or glass or even just air. They're the total opposite. They're really bad at it. We call them poor conductors, or you've probably heard this word, insulators.
And we actually use these insulators constantly. That ceramic mug you're drinking your coffee or tea from, it keeps it hot because porcelain is a terrible conductor, so it slows down the heat's escape route. And this is super clever. You know how some bricks have holes in them? That's not just to save material, it's to trap air. And since air is a really poor conductor, it acts as a layer of insulation, helping to keep our houses warmer in the winter and cooler in the summer. Pretty smart, right?
Okay, so that was conduction. Let's move on to method number 2, convection. This one is completely different. It's all about how heat moves through fluids. And when we say fluids, we just mean liquids and gases.
And I guarantee you've seen this a million times. Think about when you light an incense stick, or even just a candle. The smoke doesn't just spread out sideways, does it? Nope, it rises. Why? Because the air right around the flame gets hot. It expands, becomes less dense, and starts to float upwards. And it takes the smoke along for the ride. That one simple observation, that's the heart of convection. So here's the huge difference from conduction. Remember how in conduction the particles just passed the energy along? Well, in convection, the hot particles themselves actually move. The hot, less dense stuff physically rises up, and the cooler, denser stuff sinks down to take its place. This creates this constant circular flow, a current. It's heat transfer by actually moving the hot stuff around. And this isn't just about a little bit of smoke. This process happens on a massive, epic scale in nature. And it's all driven by one simple fact. Land heats up and cools down way faster than water does. Just remember that, because it's the key to some huge convection currents in our atmosphere. And what does that give us? The sea breeze. Here's how it works. During the day, the sun beats down, the land gets hot fast, it heats up the air right above it, and what does that hot air do? It rises. So now you've got this space, an area of lower pressure over the land. Nature hates a vacuum, right? So the cooler, denser air that's been sitting over the sea rushes in to fill that space. And that is the refreshing breeze you feel at the beach. It's literally a giant convection current you can stand in. All right, on to our third and final method, radiation. Now, this one's the weird one. It's special. Why? Because it doesn't need any particles, any solids, liquids, or gases to travel. It's just pure energy zipping through empty space.
I mean, just think about the sun for a second. It's millions of miles away, and between us and it is the freezing, empty vacuum of space. There's nothing there to conduct heat, and there's no air to create a convection current. So, how on earth do we feel its warmth? Yep, you guessed it. The answer is radiation. Basically, radiation is heat that travels as waves, kind of like light waves or radio waves. And here's the thing. Everything that has a temperature is giving off these heat waves. When you take a hot pan off the stove, sure, it's heating the air around it, but it's also just beaming heat out in all directions. That's radiation. And this right here is exactly why what you wear matters. In the summer, you wear light-colored clothes, right? That's because light colors are great at reflecting the sun's radiation away from you. But dark colors, they do the opposite. They're amazing absorbers. They just soak all that radiation up, which is awesome if you're trying to stay warm in the winter, but not so great on a hot summer day.
Okay, so let's do a quick recap. We've got 3 modes. 1, conduction. That's the domino effect, particle-to-particle transfer. It needs stuff to travel through, mostly solids. 2, convection. This is when the hot stuff itself moves, creating a current. This happens in liquids and gases. And 3, radiation, the weird one. Pure energy waves that don't need anything to travel through.
All right, now for the grand finale. This is where it all comes together. We're going to see how all 3 of these methods, conduction, convection, and radiation, work together in this beautiful, grand synthesis to power one of the most important systems on our entire planet.
And what am I talking about? The water cycle. That whole process of water moving from the oceans up into the sky and back down again, it is driven from start to finish by heat transfer.
So let's just walk through it. It all starts with the sun's radiation. Those energy waves travel through space, hit the oceans and lakes, and heat up the water until it evaporates. Okay, so now we have this warm, moist water vapor. It's less dense than the air around it, so it rises up through, you got it, convection. As it gets higher and higher, the air gets colder, causing that vapor to cool down and condense into clouds. And finally, once those clouds are full, the water comes back down as rain or snow. It's an incredible symphony using all our methods of heat transfer.
So here's the big takeaway. Heat transfer isn't just some small-scale thing, like a hot pan or a breeze at the beach. It is the giant planetary engine that powers the whole water cycle. It's what moves and replenishes all the fresh water on Earth. I mean, it is absolutely fundamental to life itself.
And with that, we're at the end. But I want to leave you with a question to chew on. Now that you know the rules of the game, conduction, convection, and radiation, start looking around. What else in your world is being secretly shaped by these incredible hidden forces? I promise you, once you start looking, you'll see it everywhere.